So this video is about the normal distribution and the 68, 95, 99.7 rule. So in class we flipped coins and looked at histograms, and we noticed that as we made more flips, the histogram tended to look kind of like this one here. So here's another histogram that sort of follows that same shape, and this one shows us the grams of Halloween candy eaten on our x-axis. And as any histogram shows, we have frequency on the y-axis. So we can see how many people ate how much candy. So if we look at all the way on the left, the little blue bar there, that if we want to read this, of course we know how. We know that that tells us that about one person ate between 65 and 67 grams of candy. We have to estimate a little bit here because we can't tell exactly, but that seems reasonable. And here we can see that about 13 people ate between 79 and 81 grams of candy. And if we look here, we can see about 72 people ate between 93 and 95 grams of candy. So that's how we read the histogram. We already know that, but it's good to be reminded. Now, if we wanted to, we could change that because, well, we could first look and see what about all of this. This is everybody, so what does that represent? Well, if we count it all up, in total there were 1,000 people, and they ate a total of 10,000 grams of candy. I can do that by calculating what we just did, but do it with all the bars and add them all up. Great. So now that we know the total, we can go and find the mean, which is 100 grams. And we can even find the standard deviation if we had really accurate data. And for this one, the standard deviation is 10 grams. I know that because of the original data, which you don't have access to here. So with this information, we can tell a lot about what happened here with the grams of Halloween candy eaten. So remember this, we showed one person ate between 65 and 67 grams, 13 people, etc. So now that we know that there were 10,000 grams of candy eaten and there were 1,000 people eating them, well, we can calculate that this by percentage. We can say 0.1% of people ate between 65 and 67 grams of candy. We can say 1.3% of people ate between 79 and 81 grams of candy. We can say 7.2% of people ate between 93 and 95 grams of candy. So we can calculate the percentages because we know the totals. That's interesting. And because we know the totals, we can also find other percentages. We can find this percentage here. We can see what percentage of people ate between 79 and 95 grams of candy. And we can calculate that. 723 people, if we added it all up, ate between 79 and 95 grams of candy. So that would be 32.3% of people ate between 79 and 95 grams of candy. So we can do this with really any of the bars that we want. We can calculate the percentages. Let's remember that. So we could also draw a frequency distribution curve. So the frequency distribution curve would look something like this. And remember, the frequency distribution curve just shows us kind of the top of the histogram at each point. And this is really helpful to us when we have a lot of data, even more than what we have here, to be able to make some judgments about what's going on. So here we have a frequency distribution curve, and it looks like a bell-shaped curve, which is very common in statistics. We often see populations and samples that form a bell-shaped curve for the frequency distribution curve. This one in particular is very, very, very close to what is known as a normal curve. So the normal distribution is a distribution that happens a lot in nature, and so because of this, we can make some decisions. So we often have data that follows a normal frequency distribution, and let's look at it and see what we can tell. What do we notice? We notice that it's symmetrical. It looks the same on the left as it does on the right. We have a high frequency in the middle, right? A lot of people were in the middle, and we have a low frequency far away from the middle. Very few were really far away from that middle. And that's what a normal curve shows. That's what really any bell-shaped curve shows, and not all bell-shaped curves are normal distributions. So what else can we tell? What does this mean? So the mean is in the middle because it's symmetrical. The mean is in the middle, and the mean is the mode because the highest frequency is in the middle, and the mode is the highest frequency. And the mean is the median because the median by definition is the middle number. So here we have the mean, the median, and the mode all the same, all found right in the middle. We see that we have high frequencies close to the mean, low frequencies far away from the mean. So a lot of the data is very close to the mean, and very little data is very far from the mean. We still know that the mean is 100 grams. We can mark that. That's right there. It's in the middle. We also know the standard deviation is 10 grams. So we can mark one standard deviation away. So one standard deviation lower than our mean is 90. It's right there. And one standard deviation higher is 110. Two standard deviations higher is 120. Two lower is 80. And we could keep doing this. We could find how many standard deviations away from the mean at different points on our histogram, on our frequency distribution curve. So how can we use this? Well, for perfectly normally distributed data, we know something. We have this specific bell-shaped curve, and it's modeled by a function. Now, I'm going to show you this function. There it is. And you have to memorize that function. No, just kidding. I don't care that you know this function or not know this function. In fact, I didn't know it. I had to look it up. But what's important to know is that it is modeled by a particular function. We know how to graph that curve. All right, we have mu, or we have x as the value of data. That's our input. It's right there. Mu is the mean. This mean is 100, for example. Right there is where we would put that in. And the standard deviation squared is that symbol right there. We know the standard deviation is 10, so the standard deviation squared is 100. And so we could put that in there and there. So essentially, if we put in 100 grams for the mean and 100 grams squared for the standard deviation, then if we graph f of x, we'll come up with the curve that you see, the frequency distribution curve on the left. That's what it'll look like. That's what the graph of that function looks like. So if we wanted to find a point on that curve, we could just plug it in to our function and we could find what the output is. Okay, why is this interesting to us? Well, it's interesting because that means that if we have perfectly normally distributed data, we can make predictions about that data. We know what the data is going to look like. So we can use that information. We can predict the percentage of the data that lies in a particular range. So, for example, the easiest one to see is that 50% of the data falls below the mean, right? This is symmetrical, the mean's in the middle, so half the data is below, half the data is above, so we can see that 50% of the data falls below the mean. That's easy to see. There are some other percentages that are not so easy to see, but because a normal distribution curve has a known function, with a little bit of calculus, we can figure out some other percentages. I'm not going to ask you to do the calculus, but I am going to ask you to remember some of these percentages. So, we can predict less obvious percentages. We can predict how much data is within one standard deviation. So in this particular example, we're looking at how much data is between 90 and 110. How much data is within one standard deviation of our mean? And again, because we know the function for the curve, we can do some calculus and we can figure out that 68% of the data falls within one standard deviation of the mean. That's true for all normally distributed data. If we have a normal distribution that describes this data, 68% will fall within one standard deviation of the mean. Now, We'll never get perfectly normally distributed data. But if we get close to it, then we can use that as an approximation. And we can say that, okay, this data seems to be normally distributed. And we can say that around 68% of the data is within one standard deviation of the mean. We can also say that 95% of the data falls within 2 standard deviations of the mean. This is always true for perfectly normally distributed data. Always. So between 80 and 120 in this particular example, 95% of the data is there. Within 3 standard deviations of the data, we find 99.7% of the data. That means only 0.3% of the data falls outside of 3 standard deviations from the mean. And of course, we can use this with probability. So what is the probability that a piece of data falls within 3 standard deviations of the mean? Well, the probability is 99.7%. Because 99.7% out of the 100% falls within 3 standard deviations of the mean. Now, I know I've said a lot of complicated things. One thing I do want to point out to you is that all the way on the left and all the way on the right, there is some data out there. There's a little bit of data out there. So don't think that all the data is within 3 standard deviations of the mean. In fact, 99.7% is. So that's key. So sometimes on our graphs, it's hard to see that. But just remember that 100% of the data goes on forever to the right and forever to the left. But 99.7% is within 3 standard deviations. Now, going back, I know I've talked a lot. I don't care that you understand that function that I gave you. I don't care really if you completely understand how to use that function or anything like that. What I care about is 2 things. One is that given a histogram, we can figure out percentages that fall within particular ranges. And with perfectly normally distributed data, we can predict how much data is within various ranges. Specifically, I want you to memorize the fact that 68% of normally distributed data is within 1 standard deviation of the mean. I want you to memorize that 95% of normally distributed data is within 2 standard deviations of the mean. And I want you to memorize that 99.7% of normally distributed data is within 3 standard deviations of the mean. I want you to memorize these facts, and because we're going to use them. And in fact, a lot of what we make decisions about are based on this rule. This is known as the 68, 95, 99.7 rule. Mathematicians are very creative with that name. So remember it, use it, and understand that the reason we can know this is because we know the function of the distribution curve. And so we know how high each of the little bars of the histogram would go, and therefore we can calculate the percentages. I know this may be a little bit confusing to you. Make sure you memorize these 3 parts, 68, 95, 99.7, and we should be good.